Welcome to 2026 3MT at Case Western Reserve University. This is, believe it or not, our 5th year of doing this. So we're really excited. I know this is definitely one of the days I look forward to over the year, and I can see from a lot of your faces, a lot of you are excited or nervous maybe looking up here. So we're really excited for you. A couple of things before we get started. I actually have some slides in our kind of front part of this, and I was telling Rachel beforehand, next year we'll have to condense it to one static slide, and I'll have to keep this to 3 minutes, but not this year. So this is 3MT is a really important skill, and you may have started to understand a little bit of that now. Some of that you may kind of realize as you go forward, but it's really important from doing things like collaborating on research. A lot of the time, I'm sure on your research projects, you're working with people from different backgrounds, and sometimes it's really easy to fall into jargon because you're comfortable with maybe some of your colleagues, but it's kind of surprising, even if you step back a little bit, about how much you don't understand sometimes maybe what people are talking to you about if they're even from a slightly different line of research. So from collaborating with research to working with different team members, I think it's a really important skill. It's growing in kind of from a requirement perspective from graduate schools, and I think from an expectation from people that hire graduate students, your ability to communicate to a broader group. Also, as much change as there is in kind of politics and how society looks upon research, it's part of our responsibility as researchers to advocate for research and make sure that the community understands how important it is for us to do research and to do science. And in order to advocate for that, we have to be able to talk about it in a way that everyone can understand it. So it's also, I feel like it's part of our responsibility as scientists to be able to do this. The 3MT program started by the University of Queensland in Australia in 2008, so it's a little older than our 5-year program. It's now held at over 900 universities across more than 85 countries. As you know, today is our final competition, our finale at Case Western Reserve University. It's our second round. So we had a first round that was all online. We have this in-person event, and the winners from today's competition will go on to a regional and hopefully national final. This is hard, right? How many of you have done a 3MT before? A few of you? Okay, it's hard. And it's hard because it's an uncomfortable thing for a lot of us to do, right? Some of us aren't comfortable with public speaking. Some of us aren't used to speaking to kind of like in a different way. We're standing here, no podium, no slides to hide behind. The focus is you. It's not your slides. And so it's just a little different. But I can assure you, I've seen and heard about all the practice that you guys have been working on. I was amazed by just walking in, seeing people rehearse. You guys are ready for this, I promise. And everybody that is here because they want to see you be successful. So everyone in the audience is supportive. We all just want the best for you. So I know you're feeling nervous, but really there's no reason to be nervous, okay? So just get up here, rely on all the practice you've put in, and everything is gonna go great. The other people in the audience can help, as difficult or as nerve-wracking as this can sometimes feel, it gets worse when you have distractions, right? So we can all help by making sure that our phones are on vibrate, making sure that, while someone's giving a talk, we're not coming and going. If we have to get up to go outside for any reason, that's fine, but please try as much as possible to do that at the breaks. A couple of rules now. So the rules are that this competition allows you to have one single static slide. As I said, the focus of the competition is really on the speaker and how they give a presentation. So presentations are spoken word. There's no videos, no props, nothing like that. A little bit on the judging. So judging is really done around 2 domains. The first domain is comprehension and content, and you've all seen the judging criteria before, so I won't go into too much detail. And the other area is around engagement and communication. So all of our judges are going to be scoring you on those 2 domains, and you'll get some feedback from us afterwards about what your scores look like for each of those 2 domains as well. We're really excited to have the judging group that we have here. It's a really esteemed judging group, and I know they're all really excited to see your presentations as well. Most of them have been doing this for several years, some of them since the first competition. It's the same group coming back and back because they love it so much. So again, they're here to be supportive of you. A little bit on the structure. We're going to have 3 blocks with a few presentations in each blocks. Between each block, we're going to have a short networking break. And you'll see if you look along the back of the room, we have 7 tables. Those are aligned with the presentation number. So if you look at block A2, presentation A2, sorry if I called you out, A2. Who's A2? All right, A2. So A2 is going to be at table 2 after the first block. And so we don't unfortunately have a lot of time for questions. We don't have any time for questions after each presentation, but we'd love to have you engage with everyone. So go find A2. She'll be right back over there after the first block. And then we'll do that after each block. We'll also have a People's Choice Award after each block. You'll see a QR code come on the screen. Please, before you get up and move around, scan that and give us your vote. You all are the judges for those. And right before we get to the end, we'll have a mini keynote, and I'll tell you a little bit more about that when we get to it. I'd like to just take one quick second to thank some of our sponsors, and you'll see them here and on the back of your agenda and probably a few other places throughout the program. The Veal Institute, the School of Graduate Studies, the Spoken English Language Program, and the Case Coulter Translational Research Partnership. So we're going to get going. Really excited. Actually, I did miss something. What I wanted to do is have everybody relax for a second. So why don't you stand up? Everyone stand up. I know this is hard. And just take 30 seconds to introduce yourself to the people that you're sitting at the table with. When you're speaking up there, you're going to see 2 monitors. One side is your presentation, and the other side is a timer. We'll start the timer when you start talking, right? So don't worry about it. Just get up there, take a deep breath, and when you're ready to go, just go.
Okay, thanks, Steve. First up, we have Christiana Leah, a fly solution to stabilize and maneuver.
Hi, my name is Christiana Leah, and I study fly sensory feedback systems. In this case, this is a crane fly we caught actually at the university farm this summer. Luckily, the flies that we work with aren't quite this big in real life. But I'm going to tell you about kind of first an analogy with our own systems. And we have our inner ear that serves to monitor our balance. So our position, our velocity, how we're moving through space. It keeps us stable and it detects how your head's moving and how your body's moving. And now if you think about if you take your inner ear and put it on your hips, so it's right near your legs, your arms, kind of your motor systems, that's a lot of what flies have done. So they've evolved this haltere, which is a gyroscopic organ, and all flies are united by this haltere, where they generate 100% of their wings, or 100% of their lift with their forewings. So anytime they fly, it's all in their first pair of wings. The haltere functions purely sensory. So it senses inertial forces like position, velocity, acceleration, how the fly is moving relative in space and time. And I'm going to talk to you today about 2 different pathways that I've worked on. The first being the haltere to the legs, and this is a new sensory motor pathway that we found. The second being the haltere up to the wings and to the head in flight. So that first one is highly relevant to the crane flies. They're not very likely to take off. Instead, they're having to maintain a stable posture. So a leaf for us might be pretty, but for them, that's a tremendous amount of movement. And so we found that when the center of mass moves relative to its legs, it kicks a signal up to its haltere. It turns the haltere on, so the haltere will start oscillating. If the body moves more, then the haltere will oscillate bigger and faster. And in turn, that haltere kicks back to the legs, where if the fly falls and it has to bring itself back up, the haltere informs it, how do you move? If you're rotating like this, how do you counteract any of the movement? And the second pathway is actually in flight using a different fly. So it's a fruit fly that its whole body is the size of that single haltere. So it's a much smaller scale, and they flap 200 times a second. So anytime that fly has to make a stroke-to-stroke modification, it has to be done in under 5 milliseconds. And so we have looked at this haltere kind of as a joystick, like in a video game. If you move your joystick, your whole character is going to move. We use the genetic tools to actually move that haltere around. That drives changes in the wings and the head that functions on this 5 millisecond time scale. And so overall, my two pathways and these two behaviors highlight a tremendous amount about how they rely on rapid mechanosensory feedback to maintain both stability and maneuverability. Thank you.
Next up, Sadia Ferdaus. Can we use shoe sole dust as a measure for outdoor microbial exposure?
Think about your last one, maybe around your neighborhood, across campus. Every step, your shoes picked up tiny pieces of the world around you. Dust, soil, and millions of invisible microbes. Why does this matter? As more and more people are growing up in cities at the same time, asthma, allergies, and other immune-related diseases are rising. Biodiversity hypothesis offers an explanation. We are missing the early life exposure to diverse microbes that help train our immune system. But research findings are conflicting. And one major reason is most studies don't actually measure the microbes people encounter while outdoors. Indoors, we have robust methods to measure microbial exposure, but we lack a simple comparable tool for outdoors. So we asked, what if our shoes could measure it? Shoes go everywhere we go, recording our environmental exposure. To test this, we collected dust from shoe soles after walking in 3 different environments. And we call them urban gray, that's mostly on pavement, urban green, pavement and park mix, and rural green, exclusively forest paths. Then we analyzed the DNA from the dust to see which microbes were there. And here's what we found. The method works. The left and right shoe from the same walk had nearly identical microbial communities, showing this method is reliable. Also, the shoes really reflected the environment. Rural green paths had diverse, richer microbial communities compared to the urban ones. And it wasn't simply urban versus rural. The amount of green area along the path was strongly linked to microbial diversity. This simple shoe sole dust method gives us something we have been missing, a practical, scalable way to measure real-world outdoor microbial exposure. And the next step is to uncover how this exposure connects to our immune health, because the key to understanding our health might be right under our shoes. Thank you.
Next up, Tarabat Kadai, energizing immune cells to fight solid tumors.
Hello. This is the picture of Emily. Emily was dying when she was 6 years old. She had leukemia, chemotherapy failed, and her parents were told to prepare for the worst. Then, doctors at the University of Pennsylvania tried something totally new. They took her own immune cells, genetically reprogrammed them, and sent them back to her body. That treatment, cell therapy, saved her life. Now, 10 years later, she's still cancer-free. For a moment, that treatment felt like the future of the medicine. Startups raised everywhere, and everyone thought cancer is finally cured. Not only cancer, we can train immune cells to fight against autoimmunity also. But here we are, this many years after. The reality is, cell therapy only works in blood cancers, and only 20% of the patients are responders. It fails in all the solid tumors, which make up to 90% of the patients. And the manufacturing cost is too high. It costs $500,000 per patient. But why? What is the problem? Imagine you are making the most powerful cancer-killing cells in the world and sending them in a battlefield with no food, no nutrient, and no support. This is exactly what happens when our immune cells are in a solid tumor environment. Our immune cells are getting exhausted. In my work, we aim to answer this core question. What if we provide our immune cells with internal constant energy support? We aim to address the core limitation of cell energy and exhaustion. We developed a formulation that can directly support immune cell energy. It can improve metabolism function, increase cell expansion, and help cells persistence in solid tumors. By being able to optimize immune cell energy, we were able to increase the yield, reduce the manufacturing cost, and increase the functionality in both solid tumors and autoimmunity. 10 years ago, we believed genetic engineering alone would cure cancer. Now, we know something deeper. Sometimes, curing cancer isn't about fighting harder. It's about giving our cells the energy to keep fighting. Thank you.
Next up, Annalise Hudson, A Powerhouse Divided, Using Structures to Understand Mitochondrial Fission.
Hi, I'm Annalise, and my favorite component of the cell is the mitochondria. Mitochondria produce energy. Energy that lets you embrace a friend, dance to the music, think about your to-do list, and this one's important, breathe. So as you might imagine, mitochondria are extremely important in the making and maintenance of you. Now, we normally imagine mitochondria as little bean-shaped organelles, but in fact, they form these vast networks. And these networks are dynamic. They have, if you can imagine a lava lamp, rising and falling, merging and dividing, that's what mitochondria look like in the cell. So when these mitochondria merge or fuse and divide or undergo fission, that's in response to cell signals. Mitochondrial fusion and fission is an important balance, and when it's dysregulated, the network is really struggling. And so fusion of mitochondria encourages energy production, but too much fusion results in a big dysfunctional blob. Fission, on the other hand, rids the cell of diseased mitochondria, but too much fission results in a fragmented network that's unable to produce enough energy. Too much fission is a problem in diseases of the brain, including Parkinson's disease, Alzheimer's disease, and ALS. The tiny mitochondria can't keep up with the enormous energetic needs of the brain to think, to breathe, to move and dance. And so, in order to treat these patients and restore power to the brain, we need to better understand how mitochondrial fission is regulated. My work uses powerful electron microscopes to view the process of mitochondrial fission and understand and identify drug targets. Now, it's crucial to understand these different components of mitochondrial fission so we can understand how they're interacting, which proteins are actively circling around the mitochondria and squeezing it, which proteins are encouraging or preventing fission. I use images from the microscopes to understand and determine the structures of these proteins, the shapes, that we can carry out their roles. And so much like a chair is structured for sitting, these protein structures also inform their function. And so my work has provided novel insight on how proteins that are regulating mitochondrial fission are able to cooperate and squeeze the mitochondria or shapeshift a bit into a more singular form that's unable to cooperate. And this form of self-regulation provides an excellent starting point for designing a drug to bring mitochondrial fission levels back to normal. So if we can bring balance back to this powerhouse divided, then we can provide energy to the brain and allow these patients to continue thinking, breathing, and dancing. Thank you.
Next up, Anisha Avasti, How Studying Space Saves Lives.
Right now, at this very moment, millions of particles from deep space are passing straight through the Earth, straight through every single one of you, no matter where you are on the planet. You don't feel them, you can't see them, but they are everywhere. These particles are called neutrinos, tiny, invisible particles that carry information from some of the most extreme places in the universe. By studying them, we learn how stars explode, how matter forms, and how the universe began. But detecting neutrinos is incredibly difficult. They almost don't interact with anything. So how do you go about trying to capture something that is this elusive? Physicists build giant detectors, and they fill them with special gases that are designed to capture the weakest possible signals. We place these detectors deep underground in abandoned mines because it's quiet there, similar to how you would go to an empty room to take an important call in a noisy environment. The problem is, most of the detector gases being used in experiments today are rare, expensive, and hard to scale up. My research is about finding new detector gases that are cheaper, more accessible, and more sensitive, which means we get better signals for a fraction of the cost. But there's another challenge. Many of the most promising detector gases are toxic to humans. Therefore, I build safe, sealed systems where we can test these chamber gases against thousands of voltage and in extreme conditions of temperature and pressure before they are ever deployed underground. This is the how of my research. Now, you might be wondering, oh, that's cool, but why is this relevant to me? Why does this matter beyond astrophysics? And the answer is simple. Because neutrino detectors are also used in medicine. In CT scanners, X-rays, MRIs, doctors rely on radiation detectors to see inside the human body and to deliver the right dose of radiation to the right part in the body while protecting the surrounding healthy tissues. Better neutrino detectors lead to better radiation detectors for treatments. So when I build these safe, sealed systems for testing test gases, I'm not just studying distant particles from space. I'm combining physics and engineering to advance healthcare. So when it comes to building test stands, whether I'm studying space physics or you're thinking about patient care, my research turns invisible particles into life-changing information for every single one of you, no matter where you are on the planet. Thank you.
Next up, we have Kartik Lukatia. Can immune cells see the disease?
Hi everyone, I'm Kartik Lakhotia, a third-year graduate student at Johnson Masajuski Laboratory at Cleveland Clinic Research. And I study aplastic anemia, in which the immune cells attack the hematopoietic stem cells that produces the blood. The clinical problem is that we often don't know what immune cells are targeting. So often, treatment is trial and error. Now imagine a body just like a vast airport. Immune cells are security. And every cell, just like human being, must show an ID. In our case, protein fragments go outside the cell surface, act as passport. To that, what I mean is immune cells scan these passport and decide the cell's fate. If they think this passport peptides looks normal, they move on. If they think it looks dangerous, they attack. Now the current state of medicine relies on the flight ticket, which acts as a proxy for these passports. To that, what I mean is that we rely on DNA and RNA-based tests and assume that's what immune system sees. But that's totally not true. Immune system reacts and responds to the peptide passports. Two things can happen when we miss this peptide passport. In aplastic anemia, immune system can actually attack the normal cells, that is misfire. And secondly, our immune system can be tricked and fooled, and the clones can evade the immune system and persist. And I fixed that problem. My research in immunopeptidomics fixes this problem. I scan these tiny fragments which actually immune cells sees. To that, we, in the end, measure the immune visibility score and can tell if it's attacking the cells or not. Secondly, we can actually find the precision targets to which immune system is reacting to. In the end, I would like to say, if we can measure the immune visibility score, if we can find the peptide target which is causing the autoimmunity, we can find the trigger, and we can escape the attack. If we can find, in the end, the target, we can escape the attack. And to that, I say that instead of scanning the flight ticket, let's scan the passport. Thank you.
Aditi mucho pade. Can't make it, can't perfect it, or can we?
Where do we all think the best and most advanced chemical factory on Earth is? Is it Germany or is it China? Maybe somewhere in the US. That's a trick question. In fact, we are surrounded by it right here in this moment. I'm talking about bacteria. Molecules made by bacteria have been our source and inspiration for some of the most powerful antibiotics, cancer therapeutics, and life-saving drugs. Bacteria are able to make these molecules in a matter of days, while we humans would need months, if not years, to replicate that kind of intricate chemistry. Could we use bacteria to make medicine? My research is not only about finding new drug molecules from bacteria, it is also about finding how bacteria make these molecules. So far, I've found 3 new molecules. One of them has a chlorine on it, the same chlorine and table salt. But did you know that adding chlorine to a drug molecule can make it up to 1,000 times more effective? The same chlorine and table salt, and there are about 250 FDA-approved drugs with a chlorine on them. Now imagine finding the perfect drug, one with little to no side effects, but if only it was a bit more stronger. You could add a chlorine onto it, but hey, that's still really hard to accomplish using traditional methods in chemistry. The bacteria that I work with has this machine. We need help from a 3.5 billion-year-old alchemist. To find this machine, I have to look at the DNA of the bacteria. But finding this machine that adds chlorine onto molecules is like finding a needle in a haystack. I have to use different computational methods, and after going through lots and lots of DNA sequences, I have finally found it. Right now, I'm working on asking bacteria to make this machine for me with the help of the code, the instruction manual. And I'm working on testing this machine's ability to add chlorine onto molecules and drugs. Because when we harness nature's chemistry, we're able to make drugs that we haven't been able to make before. How do we plan on delivering life-saving medicines to patients in need if we cannot even make them? Thank you.
Next up, Purba Biswas, From Patterns to Viral Shells.
Imagine trying to build a perfectly round structure without any instructions, without any glue. But nature does this every day. Viruses build protective shells around them, and so that just following some local connection rules. So my research asked this question: can mathematical patterns help us understand how viral shells build themselves? Think of a tile. Each tile is surrounded or touches its neighbors, right? So if we want to follow the same pattern of the placement rules, it will emerge as a big complex structures or a big tile pattern. In the similar way, viruses can build their protective shells. So how does this happen? So the individual proteins don't know what the final shape is. So what we are looking is how they can connect with each other and create the junctions so that they can be complex structures. In my research, I use network-based analysis, mathematics, definitely specifically, graph theory to understand how they can be self-assembled, how they can make patterns, and how the mathematical patterns can help us understand the hidden rule of viral shells. So if you want to fold a flat surface and think if that is a spare, how can we understand how that works? So here is the key idea. The key idea is local choices can create big global outcomes. And if we find the key rule to understand for what pattern it can create the area or the shell, we can design, or maybe we can get a final virus shell. So the main question is, why does this matter? We can apply this to find better nanoscale capsules for targeted drug delivery. So from patterns to viral shells, we can study virus, their pattern shells, and we can understand natural biological structures. Thank you.
Ganyu Wei, empower parents of kids with brain injury.
So why do people wear helmets when they play sports or ride a bike? To protect their heads from injuries, right? Those injuries are called traumatic brain injuries. Every year, 69 million people sustain traumatic brain injuries. And that is about 6 times the population of Ohio and 185 times the population of Cleveland. Traumatic brain injury is the leading cause for disabilities in children. It can cause troubles in talking, thinking, behaviors, and so many other skills. For children, it doesn't just affect the skills that they have already learned. It alters their development for their lives. Over the past few decades, research has made significant improvements in the medical and therapeutic treatment for these kids. However, one critical group has been largely overlooked: the parents. And we know how parents do after the injury is highly related to how well their kids can recover. So have you ever been in a situation where you knew someone needed help, but you just didn't know how to help them? That's the situation of most parents of kids with traumatic brain injuries are like. They are never formally trained, and they're left in the horror of not knowing how to help their kids for decades. So research shows that when parents are trained, their confidence increases, their stress decreases, and most importantly, the skills of their kids significantly improves. However, globally, there are only 4 programs available to people with traumatic brain injury, and none of which is specifically for kids. And this leaves millions of families without access to appropriate support. And this is where my project comes in. By incorporating the voices of the kids and the parents, I'm designing an accessible and research-based treatment program that's specifically for these kids and their family members. Parents will have the opportunity to learn more about what it means to have a kid with traumatic brain injury, how to support them in terms of talking, thinking, managing behaviors and emotions, and ultimately how to help them go back to school and be with their friends. In the following semesters, I will pilot the study with real families, refine it based on measurable outcomes, and I'll incorporate artificial intelligence in the training program to maximize the learning and the application of skills at home. Because when we empower parents, we're transforming the recovery journey of the children around the world. And I believe every parent deserves the chance to know how to support their kids. Thank you.
Next up, Osis Ofumwengbi, exploring the impact of followership on leadership effectiveness, a qualitative study.
Have you ever wondered why leaders like, for example, Mark Zuckerberg, remain effective in their organizations and their organizations continue to grow? Think about it for a second. My study decided to understand how followers make leaders effective. In this case, we decided to take the focus from the leaders and look at the followers. This is what we call reversing the lens approach. And to do this, we decided to interview 41 participants in organizations and to see the ripple effect of how followers impact leaders and what are the constructive and destructive outcomes, meaning the negative and the positive side. In doing so, we analyzed 2 behaviors, the effective behaviors and the ineffective behaviors. When we spoke to this participant, what did we find? For example, we interviewed a follower, And the follower said something. I drew the data lines. I did the work. My supervisor didn't do anything, but she went in there and presented my work. We call this reputational spillover. Here, the supervisor didn't know what she did, but she took the credit of what the follower did, and she looked more competent. On the other hand, we spoke to a leader. The leader said something. I had to take her off the project because this employee didn't know what she was doing, but I was evaluated based on the project outcome. When we begin to analyze this, we realize that ineffective followers' behaviors didn't just impact leaders on the individual level. We began to see that this affected the team level, causing team cohesion and negative team climate. And on the larger level, we began to see organizational vulnerabilities and operational disruption. Then what did we notice? Leaders who had effective followers began to have improved leadership functioning, and they will have increased strategic evaluation and transformative outcome. What's our study trying to say? Effective followers mirror attributes of effective leaders, meaning that effective followers can also be effective leaders. And also, we began to realize that effective followers are capable of innovative and autonomy, meaning that they're capable of independent critical thinking. They're not just passive followers. They're not just do as I say or do as I do. If you look at my picture here, leaders are only as effective as the kind of followers that shape them. So this is the conclusion of my study, and so I'm trying to bring to the awareness that we should shift the traditional mindset and stop downplaying the kind of the importance of the employees we have in an organization, and try to give them credit for the work they do. Thank you so much.
Next up, Emma Scritchfield, using molecular mechanics to restore protein delivery in autism.
Imagine living in a city where delivery trucks can never reach their destinations. They break down, they stall in warehouses, the supplies all start to run out, and before you know it, your entire city starts to malfunction. That sounds pretty extreme, but it's actually something that can happen inside of our brains. Now, proteins are like the delivery trucks of the cell. They're built to travel to a precise location to do an important job, like controlling what comes in and out of our cells, sending signals, or helping our neighboring cells to communicate. But sometimes small changes happen in the DNA that build these proteins, and we call these mutations. And it'll subtly alter how the proteins are built. And so it still looks like a protein, but it has a broken part. And so instead of reaching its destination, it breaks down in the cell tows it away, and it never has a chance to do its job. And when enough proteins fail to show up, our brains can start to malfunction. But a few years ago, my lab discovered something pretty exciting. There are drugs that can act like mechanics, so they can fix these broken proteins, get them back on the road and to the right place. And that discovery led me to wonder, what if this mechanical protein breakdown isn't all that rare? But what if it's prevalent in common brain disorders like autism? Now, autism affects 1 in 36 kids in the US and has a really strong genetic basis. If we take a look at the DNA of autistic patients, we'll often find mutations in the genes that make up these cellular delivery trucks. And these are mutations that could cause them to stall prematurely or break down before they're ever given a chance to function. And so to take a closer look at this, I built a system that allows me to watch in real time if these proteins ever make it to their destination. It's kind of like the GPS tracker on your Amazon package. What I have found is that quite a few of these mutations do in fact cause the proteins to stall or break down and be cleared away before they can ever function. Next, I can deploy my molecular mechanics, restore protein delivery to the surface, and give them a chance to do their job. But why does doing that matter? Well, right now, we only diagnose people with autism based off of behavior severity alone, and not by all the different ways things could go wrong inside of their cells. So this means people with really different biological problems are getting the same type of treatment. If we're able to identify which mutations cause mechanical breakdown and pair them with the right mechanic, we can turn safe and pre-existing drugs into truly personalized medicine. Because when the trucks start moving again, the entire city inside of our brains has a chance to function the way that it was intended to. Thank you.
Last up in this block, we have Joel Leinbach, Embodied Learning for Polymer Science.
My research normally sounds like this. valorization of recycled polyolefins through incompatibility-driven fiber formation using multi-layer co-extrusion. How many of you did I lose? What if I could explain it in a different way? What if I could dance it? Let me set the stage. Polymer science studies how long molecular chains move, how they stretch, align, and organize. These tiny movements determine whether polymer-based materials become strong or weak, durable or brittle. Yet, these tiny motions that determine these properties are on the nanoscale, far too small for us to see or touch. We're currently teaching people, students and the community, about fundamental motions they cannot see at scales they cannot access, usually through static diagrams or equations. Now, interestingly, education research shows that when physical movement, embodiment, is integrated into instruction, regardless of age, comprehension, understanding, and retention improve by upwards of 20 to 30% compared to lecture alone. Now that statistic made me ask a question. If polymer science is fundamentally based on movement, why don't we teach it using motion? In my work, I translate advanced polymer concepts into structured physical models. I investigate whether these physical models improve understanding in polymer science education. Here's an example. Students begin by moving through the space independently, representing monomers, the building blocks of polymers. Then they link arms and organize, creating a polymer chain with structure. Then the room expands in one direction, orienting into crystalline domains. As resistance builds, students physically feel what molecular alignment does to strength. Instead of memorizing chain orientation, they experience tension. Instead of abstract crystallinity, they embody organization emerging from motion. To quantify this, I compare a student's understanding before and after a movement-based lesson, and compare that with sections based on traditional lecture alone. I measure changes in conceptual reasoning, not memorization, of topics like chain alignment, crystallinity, and mechanical response. This work aims to shift the goal from memorizing terminology to reasoning about dynamic systems. And here's the punchline. Polymer science is based off of movement at the nanoscale, and my work looks at whether human motion at the visible scale can help us understand it. If we need deeper understanding into invisible motion, turns out we might need visible motion in our classrooms. Thank you so much.
Next up, Lushine K. Turning your own cells into a cure.
Before my talk, I would like you to take a moment and think. Do you know someone in your life have diabetes? Maybe a parent, a grandparent, or a friend your age. For those people, checking blood sugar and taking insulin are part of their daily life. And globally, over 500 million people live with diabetes. It's very common, but right now, we still have no cure. So what is happening inside the body? It comes down to a special cell type called beta cells, located in your pancreas. They are responsible for insulin secretion. However, in diabetes, your body destroys them by mistake. If that happens, you will have your blood sugar rise. You may feel dizzy, shaky, or have blurry vision. My project comes to fix this problem. We focus on generating strong beta cells outside the body that could one day cure diabetes. In the lab, we collect cells from patients and guide them to become new beta cells. However, there's a catch. Those cells kind of stuck at the teenager stage. They look right, but they don't fully function like adults. So let us ask the question, what are real beta cells doing that our lab cells are not? By comparing the gene in the real beta cells and our lab cells, I found a key gene that is missing in our lab cells. So in the step 2 of our solution, I tried to turn this gene on, using genetic tools and drugs. The results were very exciting. First, I found the beta cell number increase. Second, the beta cell function, which can be reflected by insulin release, increased by nearly 50%. This is not a small step. It's a leap towards a fully functional beta cells, ready to be transplanted. Why does this matter? Because real beta cells do not just flip a switch. They can adjust insulin in real time to match the blood sugar level. Helping those cells grow up means better diabetes treatment. Fewer spikes and crashes, fewer injections, more control. For those families who are constantly worried about the blood sugar level, This stability can be life-changing. Here's one more thing. Let's imagine if you were a diabetic patient. You can never simply enjoy a party because you have to focus on your blood sugar level all the time and always be ready for next injection of insulin. But luckily now, in the lab, we are helping those cells grow up strong and reliable that could one day cure diabetes. Thank you.
Next up, Nima Farouzi. Does mechanical loading make cartilage?
If you do nothing but live, just simple living, you are still prone to cartilage erosion. 1 out of 2 or even 2 out of 3 people are affected by serious cartilage lesion after age 55. This cartilage lesion called osteoarthritis. Osteoarthritis alone affected more than 35 million people only in the US. My grandma was one of them. She had osteoarthritis in her knees. Painful, right? And the unfortunate part is there is no permanent treatment for that. My name is Nima Farouzi, and my research is solving this problem. I make cartilage in the lab and transfer it back into the body. In my work, I introduced 2 important elements to accelerate cartilage formation. One is bioreactor, and the other is mechanical loading. A reactor is a container which can be as big as this room, but bioreactors are a small container, and the one I'm working with is as small as this. Bioreactors create body-like conditions for cells to differentiate toward the cartilage, but that is not enough. We also need a stimulant to accelerate this process. And here is the second part comes in, mechanical loading. Think about that. Why mechanical loading? Remember your childhood. When you were a kid, you moved a lot. Running, jumping, playing, all these activities helped your joint to grow nice and strong. I use the same concept here. I added mechanical loading to the bioreactor to improve cartilage quality. Here is the big picture. The ultimate goal of my project is to create cartilage in a completely sealed system, meaning that I load the matrix from one side, bioreactors handle everything inside, and I harvest a finished piece of cartilage on the other side. This finished piece of cartilage can be customized for each of you, for people who have osteoarthritis, for people who have been injured, and all of us while getting older and older. I wasn't able to help my grandma before she passed away, but now I can help your grandma. Thank you so much.
Next up, Jianpan Antarasen. Travel through the extracellular matrix, a nanoscale biological maze.
We all have that blue network there. That's the collagen, and it is the most prevalent components of the extracellular matrix, or the ECM, the ever-changing space between cells. The ECM is a real-life version in nanoscale of the maze in the movie, The Maze Runner. The maze constantly moving, blocking the runners to get their way to defeat the villains. In our body, the drugs engulf our runners. They are trying to make their way through the ECM to go to the targeted disease cells, the villains. But the ECM is full of collagen, and it is moving all the time. And also crowded with the constantly moving proteins. They trap and block their way for the drugs to move through the ECM, so preventing them to get to the targeted disease cells. We spend $2.2 trillion every year developing drugs, but we lack the precision to ensure that the therapy effectively get to the disease cells. My research is simple. We just want to understand how the ECM impedes the drug movements. We can try to watch the ECM moving in space with a microscope, but there's a problem. Those drugs are moving fast and it's random. So it appears a total blur. Moreover, the ECM itself is transparent and invisible, so we cannot see them, but we need to know the structure. I developed 3-step solution using the fluorescent microscope. Step 1, we tag the runners, the drugs, with the fluorescent protein. It's like giving a tiny flare to every runners. Step 2, we use a high-speed camera to detect every flare, even the faint or the blur ones. Step 3, we look at the similarities of the flares. This is called the correlation over time. If the flare stays steady, it means that it's stuck, removing a dead end or wall. If the flare moves rapidly, it means that they mark an open lane for them to sprint. And if we analyze every trace of the flare, we will get we will transform the blurry video into the super resolution map, the map that will show you the open lanes, the walls, or the dead end, much like the green track you see there on the screen. If we repeat this process for many combinations of drugs and ECM components, we are creating the library of data. And with that data, we can model the runner's movements. And this knowledge will be helpful for us to design drugs that can be useful for the runners, the drug that can be useful for us, and that bypass the biological barriers and improve the therapeutic outcomes. Thank you.
Next up, Cassandra Lopez, solving the hearing care puzzle with AI.
Buenas tardes, good afternoon. I'm Cassandra Lopez, a bilingual speech-language pathologist and a second-year PhD student in communication sciences. Picture this. You're sitting in a busy restaurant, dishes are clattering, people are talking over each other, and you keep leaning in saying what over and over again. It's frustrating and it's exhausting. And for many people, these types of experiences is what brings them to an audiologist. Beyond the familiar beeps of a hearing test, audiologists use speech recognition testing to see how well a person understands speech in the presence of noise by asking them to listen and repeat back what they hear. These tests capture real-world listening challenges and reveal crucial puzzle pieces on how someone hears in their daily life. But for the 67 million people in the US who speak more than one language, or for non-English speakers, often these pieces go missing. This is because most hearing evaluations are conducted only in English, even when it's not a patient's primary language. But why? First, developing multilingual speech recognition materials can take years. And second, fewer than 1,000 audiologists in the US are multilingual. And 3, even when multilingual materials do exist, clinicians often lack a practical way to score responses in a language they don't speak. Let me give you a brief example. Marta is a monolingual Spanish speaker who received a hearing evaluation entirely in English. There was no Spanish speech recognition materials. On paper, her evaluation looks complete, but in reality, it was missing key pieces. An English-only test failed to capture Marta's true hearing abilities and challenges in her native language, the one that she uses at work, at dinner tables, and with her family. Without those missing pieces, her hearing profile is incomplete, leading to ineffective treatments or prolonged listening challenges. At the Speech and Auditory Research Lab, my work focuses on solving this problem by integrating AI into the different steps of speech recognition testing. First, I use large language models to generate culturally and linguistically appropriate Spanish test sentences using existing English materials. Second, I use advanced synthetic speech to create high-quality and naturally sounding recordings to replicate real-life listening conditions. Together, these tools drastically reduce the development time for new materials. Next, I will evaluate automatic speech recognition to use it as a way for scoring patient responses, trying to check if it can accurately give results as human judgment. And then together, these materials will reduce the development time for the materials. And then overall, I'm trying to advance hearing care so that multilingual and non-English speakers, like my mom Marta, have access to equitable hearing services. Thank you.
Next up, Wei Sun, Engineering Gold for Visible Cell Therapy.
Hi everyone, my name is Wei Sun. I'm a PhD candidate in biomedical engineering. Today I'm going to present my work, engineering gold nanoparticles to make cell therapies visible. Our eyes are remarkable. At the front, the cornea must remain clearly transparent for a lifetime so that we can have a clear vision. At the back, the retina converts light into electrical signals that our brain understands as sight. These complex tissues are built from cells, and their function depends on cells. However, diseases such as corneal injury can damage these cells. Once they're lost, vision often cannot return. Today, severe corneal damage is treated with donor tissue transplantation, but donor tissue is limited, and surgery is not always successful. As an alternative, cell therapy is emerging by using transplantation of healthy cells to repair the damaged tissue. However, there's a major challenge. Once the cells are delivered to the site, doctors cannot see where they go, whether they work, or whether they survive. My work, it's like tracking those cells is like trying to see a stop sign at night without its reflective coating. Even with headlights on, the sign remains dim and hard to see. My work aims to to add that missing reflective coating. I engineer tiny gold particles thousands of times smaller than the width of a human hair. At such scale, the gold nanoparticles strongly reflect the light used in medical imaging. We incubate the gold nanoparticles with stem cells and deliver the cells into the eye. To detect those labeled cells, we use a light-based imaging method similar to an optical radar that sends light into the eye and captures the reflections that return. Because of the gold nanoparticles inside the cells strongly reflecting the light, the labeled cells become clearly visible to doctors. Now doctors can track the movement of the cell, the locations of cell, and guide the treatment with confidence. My work aims to make cell therapies visible. By making cell therapy visible, I believe we can create a safer, more effective, and more reliable therapeutic method for blinding eye diseases. Because when it comes to healing, seeing what happens makes a difference. Thank you.
Our last competitor for the day is Brandy Martz, a new spin on sustainable plastics, biaxial roll milling.
343 million tons. That's how much plastic waste is generated across the globe every single year. 343 million tons of things we use every single day. Your clothes, your water bottle, the laundry basket, kitchen utensils, the list goes on and on and on. This is what 343 million tons of plastic waste actually looks like. People living in mountains of trash, drinking microplastic contaminated water, and inhaling toxic fumes from burning plastic waste. Disgusting, isn't it? Well, what do we do about it? Reduce, reuse, replace, and recycle? These are great ideologies, but rarely practical. Plastic is cheap, it's convenient, and it's inescapable in the modern world. Well, what about recycling? Unfortunately, only 9% of plastics ever made have been recycled. And of that, only 2% meet the quality standards we expect and are willing to pay for. So what do we do now? Well, sustainability is not a new issue. So what if the solution isn't either? My research uses biaxial roll milling, a metallurgy technology dating back to 600 BCE. This technology uses compression and shear to change the structure of plastic materials, to make them stronger, more stiff, and most importantly, tougher. Using this technology, we're able to make biodegradable materials that are 14 times tougher than unrolled materials. We can apply it to recycled materials to make them 3,000% tougher than unrolled recycled materials. And we can use it to challenge limitations of currently mechanical recycling methods. In mechanical recycling, blending two things together that don't want to mix gives you an unusable product at the end. This technology allows us to put blends of materials through this process and get a material that is 22 times tougher than the original material that was not rolled. We're able to create value out of trash. Now, if we're really going to go to war on plastic waste, it can't just be the materials, it has to be the processes that we're using as well. Biaxial roll milling does not use any chemicals, not even water. We don't create very much scrap, and it can be done at room temperature. And because it's been around for thousands of years in the steel industry, it's readily available and energy efficient. Now, I just want you to imagine putting one of these roll mills at the end of an existing recycling facility. That way, the next time you throw something into one of those blue recycle bins, you're not contributing to this 343 million tons of waste. You're creating something that you use every single day. Thank you.
Wow, those were fantastic, right? Everyone give everyone a hand. You know, I've talked to a few people at the breaks, and it is totally true. Every single year we've done this competition, the proposals, or the proposals, these pitches get better and better, right? It's just amazing to see how well all of you did. So thank you so much. Now we're really excited to have kind of a three-minute thesis version of a keynote speech by Samantha Stubblefield. Samantha is the Vice President of Operations at Convello Therapeutics. Convello is a case spin-out company that is in our incubator facility that focuses on improving multiple sclerosis care, and I'm sure you'll probably hear a little bit more about that. Dr. Stubblefield received a BS in biology from the University of Akron. I think that makes you a ZIP, is that right? Okay. Also has a PhD in molecular biology here from Case, so you're Spartan. Then she left the university and started her career at the Harrington Discovery Institute, eventually went to Thesis, which is a local company in town that focuses on therapeutic development, and has been at Convello since 2018, sorry. Still, almost 10 years. Does it feel like 10 years? Yes, okay. Could go one or two ways there. Over that almost 10 years, she's advanced from Director of Research to her current role. Done a lot of different things at a startup company. One of the fun things about working in a startup company is that, you know, you're doing about everything, right? So you get to see all aspects. She's actively involved in a number of entrepreneurship support programs really around the state. And she really spends a lot of her activity and time at the intersection of science and business. So I think she's a perfect person to talk to us about why these communication skills that you guys have developed are so important. Dr. Stubblefield.
First of all, I want to thank everybody for having me. Thank you, Steve, for the nice introduction. And I also want to thank all of you guys for being so brave. I do not think that there is a single chance that even though I was always a very good communicator, I would have ever signed up to be a competitor where I wasn't going to be able to rely on slides. And so in that vein, I have attempted to step relatively far away from how I normally present, which would be with lots of slides, lots of data-rich sort of graphs that I could rely on to help me bridge through, and I've attempted to embody the 3-minute thesis and go off of memory or just off of vibes. So again, thank you guys for being so brave. It enabled me to sort of step outside my comfort zone a little bit. And I wish I could tell you that that the hardest part of science will always be the experiments, but of course you guys know now that the much harder part of science is actually communicating your science, whether it's writing papers or grants, or doing your presentations in your department, where you see sort of the nerves that people get, and you also have to think on your feet, and you don't get to rely on on slides. So experiments will always fail, and they will continue to fail. And what I have found out is that the failed experiments are much easier to troubleshoot than the challenges of communication that you'll continuously face throughout your career. If you stay at the bench and your science and the experiments remain your largest problem, that's a great career path too, and it'll be a simpler career path, I think. Because as soon as you start working with larger groups of people, as soon as you start trying to solve complex problems with other people, you find that there's a lot more reliance upon your soft skills that are not whether you can pipette or whether you can calculate things well or whether your chemistry is really, really great. So I also wish I can tell you guys that the imposter syndrome or the nerves go away, and they don't. You will always feel like you're actually not the appropriate person, or you're not actually capable to do whatever that next step is. And as Steve said, my career at Convello, I came in at a director level. My job was sort of to set up a lab and recruit people in, and then build a team. And that felt very comfortable. I had run a lot of labs, I had done a lot of science, but very quickly I became somebody who was managing contracts with large pharma, managing programs with large pharma, recruiting people in and managing people, which is also something that you never, ever get taught really in grad school. And so again, I want to sort of applaud all of you guys for already stepping outside of the bench and encouraging yourselves to grow in an area that most of us are not educated in through our actual education. And grad school is, maybe 80,000 years long, or at least that's how it felt for me. And then maybe you do a postdoc, and that's another 4 years. So 80,000 in 4 years, and you leave with, an intense education in your field, or maybe two fields if you sort of stepped outside of your normal, your original scientific expertise. But that still is almost certainly only going to be a couple intense areas of scientific focus. And then you have to decide what you want to be when you grow up. And again, if you stay at the bench, maybe you will have to limit your requirement and your reliance on your extra communication skills. But it's very likely that that's not going to happen. Particularly if you are an excellent scientist. What ends up happening is that you're good at the bench, you're good at coming up with ideas, you execute your experiments well, and they shove you into managing other people. And none of us were trained to do that. And so I think what I want to talk to you guys a little bit about is sort of how I've progressed through my career and the things that I've learned, because most of what I use on a daily basis is not things that I learned at Case, at Akron, in my formal education. It's what you pick up along the way. And I think you guys, again, have already taken a huge step that I certainly hadn't taken at your stage of your career, to embrace this idea of being able to communicate and to connect with people and to distill your ideas down to a digestible 3 minutes. And again, I think that this is a relatively contrived scenario, right? One slide, 3 minutes is intense and insane, and probably not something that you'll ever have to do again. But I think that compression forces you to find clarity, and I think that was really impressive and obvious to those of us that were judging, that you guys had thought intensely about what your project was. You had thought about why other people should care about it, not just the people who are on your committee, not just the people who are in your lab, and maybe not just your friends and family who sort of inherently care about the things that you care about. So again, as Steve said, my role at Convello has started 8 years ago, and Convello Therapy. Oh, I'm in charge of this, not somebody else, so I can move this on. So Convello Therapeutics is a small molecule drug discovery company. Again, it launched out of Case Western almost a decade ago now. It sat in stealth mode, which just basically means that nobody really externally knew that it existed. And I was the third employee that was recruited in. I came from the Harrington Discovery Institute, which is again not a Case institution, but sort of a sister institution to Case under university hospitals. And there I had learned the nuts and bolts of doing drug discovery. And so then I was brought in at an early stage at Convello into a team of, I don't know, maybe 6 or 7 people. I was the third full-time employee, and there were some advisors around. And essentially none of us knew what we were doing. And so the relationships, this is going to be recorded, right, and presented. We all knew exactly what we were doing, and it was always focused on this. No, most of us had no idea what we were doing. We were learning on the go. We were relying very heavily upon each other. And so the skills that were the soft skills were also incredibly important for the success of Convello, because you can't afford to have turnover. You can't afford to fight over things that don't matter. And so you have to really rely on your ability to build relationships, communicate problems scientifically or otherwise, interpersonal, resolve them. And these are incredibly important. Communication, areas that are also quite distinctive from what you guys just did, which was more like oration or public speaking. And so the other challenge, I think, for talking about how important communication is what areas would I focus on? You know, is it the idea that you need to be able to be persuasive and pleasant and that people, you know, you're not gonna make someone wanna stand up and just walk away from you? Of course that matters. Is it that you have to appear to be intelligent enough to, you know, to be speaking about that topic? Of course that matters. But there's also so many other areas on an every single day basis that will impact your career substantially. And so I wanna just continue to remind you that you can be the best scientist, maybe even the most brilliant scientist. And if nobody wants to talk to you, if nobody wants to work with you, if nobody can understand what you're thinking or saying or doing, then it doesn't matter. And so I want to give you just a few examples within Convelo of how my career has progressed and how I've had to learn to communicate to different stakeholders within the environment of biotech. So again, I came in as a director level and I built a lab. So I had to bring a bunch of people in, I had to hire them, and I had to identify whether I thought they would be a good culture fit, whether they would work well together, whether they had the skills necessary. Another challenge in biotech is that you don't have a ton of time or money to train people, so you have to just hope that they have the skills that they say they have, and then you bring them in. And it's very different from academia, where there's a huge network of people that you can kind of offload your, you know, new graduate student to learn a new skill, or even if they're a postdoc or a new hire and they don't have exactly what you need, you can kind of send them to the lab next door to learn a skill. In biotech, that's not really possible, and you don't have the money or the time to do that. And so there was a huge component of my early part of my career of being able to read somebody. Were they lying? You know, were they serious about their resume? We did get a number of falsified resumes, and not everybody has that inherent innate talent to kind of read somebody. But I think you can build that skill, and so that's another thing I wanted to, you know, to sort of remind you, is that just as much as you practice to orate up here, to speak with no slides, you can also practice reading people. You can open your senses up and really look at somebody and listen deeply, and you will build an understanding and an awareness of what they are thinking, whether they're telling you the truth. Are they open? Are they honest? Are they vulnerable? And will that, you know, wherever they sit on the spectrum of those various things and their skill set, will they fit within your company or within your team? And if you can be the person who can read that, you can really be an asset to your company or to your lab. Even if you're running a lab, you can say, that person's really great, obviously very smart, never going to work here for whatever reason. And that doesn't mean there's anything wrong with them, it just means this isn't the right space for them. And the earlier you can ascertain that, and the kinder you can be while determining that, you know, the better you'll be at building teams. And it's something that I feel like I have always excelled at, been able to say, this person's great but not great for here, or this person's great but they absolutely cannot report to person B. You know, everything else is great, they just can't be this can't happen. And there's been a few times in my career where I've been overruled, where someone has said, yeah, I agree, I see what you're seeing, but I don't think it matters. And then of course there's been huge problems later, and then you're trying to figure out how to communicate between people who don't get along or don't like each other or don't have the same communication strategies or skill set. So if you are in the position to hone those skills, I really encourage you do so. And do it through a wide variety of people, not just your friends, but you can practice there too, but also their family. You know, who are these people? Where did they come from? What's their mom, their dad like? What are their brothers and sisters like? How did that influence my friend and their behavior? And you can start to sort of understand and you know, I don't mean to be cynical, but you can kind of start to see archetypes of people, and it'll really help you in your methods of how to communicate to that type of person. So that was the first part of my career, was sort of building this lab, or at Convelo at least, was building a lab, building this team, and building a pharmacology engine. So we needed to be able to make thousands of compounds every year and screen them through assays and decide which ones moved forward or not. And that was the easy part. The hard part was who can do it, who can handle the grind on a day-to-day basis. How do I communicate to these people how important their role is so that they don't feel like a factory worker? Particularly because I couldn't hire factory workers to do it. I needed to hire PhD level or comparable, educated, and skilled individuals. And so that communication laterally or down, I would say, was also really important. Could I describe their role within the company? Could I back it up and say, we are trying to discover a drug that can reverse disability progression in multiple sclerosis patients? Can I teach you that multiple sclerosis hits women predominantly, but also men in their childbearing or child rearing ages? Can I remind you that that is why we are doing this? You know, that this is why I'm handing you another stack of 40 compounds to run again this week. And if you can do that, what you'll find in an honest and clear and sort of transparent way of, I don't expect you to find this to be the most stimulating week of your life, but if you could run this again, maybe we'll get a little bit closer to bringing a patient to, you know, a therapy to a patient that could really help them. And if you can do that, if you can find sort of honest ways of communicating difficult or unpleasant ideas, what you'll find is that you'll get honesty, vulnerability, and clear and open communication back. And so again, I found in my career that I was able to retain really, really talented people that should have probably left, moved on to their next career, used my company as a stepping stone, and instead they stayed because they felt respected, they felt like they were part of the process, and they got to see why we were doing it regularly. As I continued to progress in my career, I also then started having to manage external collaborations or partnerships with large pharma companies. And this was a completely different type of communication. So this was lateral, where everybody was also, you know, a highly trained scientist, but we were trying to bridge two different companies and build a huge team. And I needed to continue to make sure that they felt that we were valuable and that they didn't walk away from us, because we didn't have the money to pay for this ourselves. We needed them to fund it, and so we had to appear valuable. And I genuinely believe that we were valuable, but you never wanted to let them forget it. And so how did I, you know, continue to think about what were they needing to hear from us to feel that we were valuable and that this was a good investment in of their money. In addition, as I continued to progress in my role, I started to interact more with our board members and our investors. And so this is, again, another layer of communication where you are almost certainly not talking to somebody who can go toe-to-toe with you on the science. You have to be able to recognize who this person is, what is their background, maybe do a little bit of, or a lot of research in advance of who's going to be at the room, what do they look like, what are their background, what other companies have they invested in, you know, what do they like or not like, does anybody in their family have MS? Like, you need to kind of know some of these things. That way you can then distill your research down to only the necessary details that they care about. If you spend a ton of time talking about how oligodendrocytes can be pushed into this type of cell, and this person is maybe a very successful business person, but they ran a construction company and they built skyscrapers in New York City, are they going to be able to follow along? They're going to start losing the importance of what you're doing. And if you make people bored, or if you make them feel dumb because you talk so far above their understanding level, then they're not going to want to keep talking to you. And so in biotech, making sure that people want to keep talking to you, that they understand what you're doing and they think that it's valuable, is really the key to actually getting your work funded and to continue to develop your drug to the clinic. So again, I believe that MS patients deserve something beyond just immunosuppression. I was excited to see a bunch of you guys presenting on immunology, because I have an immunology background, but you know, there are lots of really good immunology drugs, immunosuppressing drugs that help people with MS, and yet patients still have disability progression. And so if I can bring this to somebody who maybe builds skyscrapers and say, you know, you would not want your wife or your daughter or your children or yourself to lose the ability to walk or see in their 50s. And right now, even with strong immunosuppression, MS patients still might lose their ability to walk, to think, to see in their 50s, and that's far too young. And so what I want to do with my drug is to give them the chance to regenerate their myelin, protect their axons, and recapture that ability. And if you can bring someone a package like that, it's much harder for them to say, no, I don't think that's worth my investment. Okay, I'm going to move on. So again, I told you guys, that I feel strongly that our academic education, especially at Case, is wonderful, and yet I think that as you launch into your career, you will find, and I certainly have found, that there's big areas missing. And I love that this competition exists, because I think it's trying to fill a gap. But what I left from my education feeling like I was not educated on how to speak to my peers that weren't scientifically in the same space, or to communicate down. I was always educated in how to communicate to people who were extremely intelligent and their expertise was within my space, like my mentor, my thesis advisors, maybe scientific conferences where you're presenting and you can just be so smart and you can use all the jargon, and it really maybe almost makes you feel smarter to do so. But in reality, almost always in my job, I'm talking to somebody who cares about drug development or multiple sclerosis, but they have no ability to hold the same level of scientific conversation as I could. So I think it's incredibly important to think about where you can continue to practice these skills. For me, I was the first person in my family to go to college, graduate from college, certainly the first person to even think about grad school. So all through my graduate career, whenever I'd call my moms, when I'd call my grandpa, my dad, I was able to talk to them about my science, but I had to learn how to bring it to their level because I was sort of speeding down the highway away from any sort of educational, footprint that they had. I couldn't talk to them about, antigen presenting cells or dendritic cells. I had to reframe everything. And so all of the sort of analogies that you guys used were things that I did too. My grandpa was a huge war buff. He loved reading about history and war, and I couldn't care less at the time. The unfortunate truth is that as you get older, you start to care more about it, and then your grandparents are gone, so you won't get to talk to them about it. But I was able to tiptoe my way through war analogies for immunology, which I saw multiple here. And so obviously, I'm not a genius for coming up with this, but it's a way to connect to people. And so it made my family care more about what I was doing, why I had moved away, why I was in school for 1,000 years. And it allowed me to, sort of get the benefit and the gift of them asking questions from completely outside of the box. If you're presenting only to people who are in your same frame of mind, they're gonna ask questions that you already have heard before. But if your grandpa asks you something just completely outside of the box, it really has you, it gives you that gift to sort of reflect on what you know and what you think about your own project. And I also felt like I got to experience that whenever I was teaching in college at the collegiate level. So I was teaching immunology at John Carroll and CSU as a postdoc and during my early stage of my career, because I wasn't really sure what I wanted to be when I grew up, and I thought maybe it was a professor. And so one of the things that I was able to do is figure out how to teach an extremely complex subject like immunology to people who had never thought about immunology. So it's like, how do you teach them the jargon? How do you teach them the interconnection between the cells? How do you teach them the concepts? And how do you continue to break it down into a way that's helpful but not overly simplistic? And so a quote that I recently found, literally 4 or 5 days ago, but really was something that I embodied and learned during these stages of my life, is that if you can't explain it simply, it's because you don't understand it enough. And if you get caught by a question from somebody who is not experienced in this, it's because you don't know it well enough. So spend a lot of time right now, and I'm sure you guys have experienced this while you were prepping for this, is like, what are the nuts and bolts of my project? Why does my project matter? And if you've never been in front of people and gotten asked that question, you're lucky, and it'll come eventually, where someone will just ask you, like, who cares about myelin? And you're like, you have to sort of sit and go, why wouldn't you care about myelin? And you realize that not everybody's thinking about the same things you are the way that you're thinking about it. So I hope that your experience here and during this process gave you the types of insights that my experience talking with my family and teaching did, which is that understanding that you have to go deeper and deeper into your project in order to be able to communicate it effectively, particularly if you're trying to communicate it simply. And again, I thank you for inviting me here. I thank you for letting me experience and judge you guys, and for the bravery you guys have showed. And I hope you continue to utilize these same aspects of learning, which is that you go deeper and above in order to understand your project, and then you deploy them through the rest of your life as well. Learn more about your friends, ask more questions about your family members, and think about how the lessons that you learn from that will help you communicate with them better and build deeper and more significant relationships. Thanks so much. Oh, one thing, I do a lot of these with undergraduates and graduate students. So this is my actual personal email address. Case used to let you keep your emails. I don't know if they still let that, but that's still my email address, and you can reach out if you ever need anything or want to talk about Cleveland biotech scene.
Thank you, Samantha. Everyone give Samantha a round of applause. A couple of other thank yous. I want to once again just thank all of you for all the hard work that you've done in coming here together. So thank you. Thank our sponsors, very generous sponsors, the Veal Institute, School of Graduate Studies, the School of Graduate Studies Spoken English Language Program, and the Case Coulter Translational Research Partnership. Thank you. I'd like to say thanks also to all of our judges. Thank you all. And I definitely need to thank our 3MT Planning Committee, especially Rachel Begley. Other members of our planning committee were Eric Moore and Jillian White. Thank you. All right, so now we get to the fun part. We get to prizes. All right, so the scores were really close. In fact, 30% of the scores were within 1 point of the winner. Right? It's crazy. Yeah, and I could, anecdotally, just talking to the judges between sessions, they had a tough job this year, right? Because they were all really good. All right, so first we're going to start with the People's Choice Awards, and Andy Cornwell is going to come up and give those awards. Did you know you were going to give those awards? Okay. Andy is from the Case Coulter Translational Research Partnership, and also will be a surprise to him that he's going to give us a couple of sentences on what the Case Coulter program is.
So thank you. I'm Andy Cornwell. I'm the Associate Director of the Case Coulter Translational Research Partnership. The Coulter program, as it's easier to say, is a funding mechanism that exists within the university to help biomedical technologies get ready for funding outside the university. And one of the key success attributes that we see in our program is the ability of our academic teams to express their research in the terms that you guys use today. So I can't tell you enough how, again, Samantha said it so eloquently, but the ability to communicate this stuff to people outside your academic field is an absolutely critical skill, and you guys knocked it out of the park today. So we have one award for each group. Is that what this is? Okay. So I don't
call all three up.
Yeah, okay. So I'll call all three of you and come up here and we'll get a picture with Steve, okay? First, I'm going to do my best with these names. Anisha Avasti. I'll just do all three. Osas Amfumwebe. And Brandy Martz. Congratulations.
Congratulations.
Nice job. Really great presentation. Osas, congratulations. Lovely presentation. Thank you. Brandy, congratulations.
Thank you.
Nice job.
Yeah.
Come on, Scooter. All right, let's have another round of applause. Thank you guys very much. Nice job.
Thanks, Andy. Our third place award is going to be given out, that is sponsored by the Spoken English Language Program. It's going to be given out by Eric Moore.
Thank you, Steve. And this is great this year. Each year it seems like this gets better and better, and it was amazing this year. Fantastic preparation. I got a chance to work with a large group of people this year, and it was amazing. So just wanted to say, Spoken English Language Programs, I direct it, and it's located in the School of Graduate Studies. That was wonderful speaking there. And we service people on campus who are non-native speakers of English, whether they're international students or postdocs, professors, staff, etc., or if they're just non-native speakers from here in the US. So we do language training, cultural training, etc. So most importantly here, for third place prize goes to Emma Scritchfield.
Thanks, Eric. Okay, so the scores were tight overall for sure. They were even tighter at the very top, all top three. The second place prize had a final score of 12.54545454, and the first prize had a score of 12.54545454. First time we've ever had a tie, right? So we're going to award 2 first prizes this year. We'll split the prizes between 1 and 2, and we're going to have to come up with a tiebreaker in the future to see who goes on to the next stage, because we're only allowed to send one person forward. So I'm going to invite up Rachel Begley from the School of Graduate Studies and Mindy Barrow from the Veal Institute of Entrepreneurship to give out our first 2 awards. And I think Mindy's going to start by just telling us a little bit about the Veal Institute.
First, I want to applaud everyone who participated. I know we sound a little like a broken record. The other organizations here today, our guest speaker, Samantha, I'll say the same thing. The story that you tell is really critical. And it's easy if you have unlimited words and unlimited time. It's really hard when you have to say it in very few words or in a very short time frame. So applause again to your effort. It will pay huge dividends regardless of the outcome today. With respect to the Veal Institute for Entrepreneurship, we live over in ThinkBox. Come check us out. We have funding programs. Our next event is the Morgan Thaler Pavey Startup Competition. There may be some folks here participating in that. That's a $45,000 cash prize that goes out to students or alumni 5 years or less from the university for an idea track, a venture track, or a social impact track. We coach and mentor startups one-on-one, faculty, alumni, PhDs, postdocs, students, so come find us. We have micro grants. They're closed for this year, but for those of you still around next year, they are open. They are no strings attached, maybe a few photographs on LinkedIn, quick report. By report, I mean paragraph, right? On what you're doing. But other than that, there's no dilution. There's no expectation you spin anything out. Just start to explore. So come find us. My name's Mindy.
Thank you, Mindy. I'm Rachel Begley. I direct the Graduate Studies Professional Development Center and have been working with the 3MT program for 5 years. This is our 5th year. And I just want to thank all of our competitors. This started back in the fall. All of the work that they have put in to do the video round. We've had many, many practice sessions, different workshops. You all have shown up, and we can tell in the work that you've done with the pitches this year. So thank you so much for the work that you put in, and let's give a round of applause to the competitors. So as Steve mentioned, we've never had this before. So this year we have a tie. So we're going to call up our first place winners. I'll go ahead and announce one name and then pass it over to Mindy for the other. So our first place winner is Brandy Martz.
And our second first place winner is Joel Leinbach. No way!
Yeah,
Congratulations!
Thank you.
Joel and Brandy are from the same department. Congratulations.
Thanks everyone for coming. I hope you really enjoyed. I hope you enjoyed this as much as I did, and I hope you have a great weekend. Take care.